So hello everyone and welcome to NEETOPEDIA, that is NEET ka encyclopedia, and we are back with our chemistry audiobooks. We had already finished the group 15 elements of the P block in the previous audiobook of chemistry, and today we will be starting with group 16 elements. There was delay in audiobooks due to some technical issues, but everything has been resolved. So now on, audiobooks will be continuous on this channel. So subscribe to the channel and stay tuned. And without wasting our time, let's get started. 7.10 Group 16 Elements. Oxygen, sulfur, selenium, tellurium, polonium and livermorium constitute group 16 of the periodic table. This is sometimes known as group of chalcogens. The name is derived from the Greek word for brass and points to association of sulfur and its congeners with copper. Most copper minerals contain either oxygen or sulfur and frequently the other members of the group. 7.10.1 Occurrence. Oxygen is the most abundant of all the elements on Earth. Oxygen forms about 46.6% by mass of Earth's crust. Dry air contains 20.96% oxygen by volume. However, the abundance of sulfur in the Earth's crust is only 0.03 to 0.1%. Combined sulfur consists primarily as sulfates such as gypsum, that is CaSO4.2H2O, Epsom salt, that is MgSO4.7H2O, barite, that is BaSO4, and sulfides such as galena, that is PbS, zinc lead, ZnS, copper pyrites, CuFeS2. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic materials such as egg, protein, garlic, onion, mustard, hair, and wool contain sulfur. Selenium and tellurium are also found as metaselenides and tellurides in sulfide ores. Polonium occurs in nature as a decay product of thorium and uranium minerals. Livermorium is a synthetic radioactive element. Its symbol is Lv, atomic number 116, atomic mass 292 and electronic configuration radon 5F146010 7s2 7p4. It has been produced only in a very small amount and has very short half-life, only a small fraction of 1 second. This limits the study of properties of livermorium. Here, except for livermorium, important atomic and physical properties of other members of group 16 along with their electronic configuration are given in table 7.6. Some of the atomic, physical and chemical properties and their trends are discussed below. 7.10.2 Electronic configuration. The elements of group 16 have 6 elements in the outermost shell and have Ns2-Np4 general electronic configuration. 7.10.3 Atomic and ionic radii. Due to increase in number of shells, atomic and ionic radii increase from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. 7.10.4 Ionization enthalpy. Ionization enthalpy decreases down the group. This is due to increase in size. However, elements of this group have lower ionization enthalpy values compared to those of group 15 in the corresponding period. This is due to the fact that group 15 elements have extra stable half-filled p orbital electronic configurations. 7.10.5 Electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. 7.10.6 Electronegativity. Next to fluorine, oxygen has the highest electronegativity value among the elements. Within the group, electronegativity decreases with an increase in atomic number. This implies that the metallic character increases from oxygen to polonium. Example 7.10 Elements of group 16 generally show a low value of first ionization enthalpy compared to the corresponding period of group 15. Why? Solution: due to extra stable half-filled p orbital electronic configuration of group 15 element, larger amount of energy is required to remove electrons compared to those of group 16 elements. 7.10.7 Physical properties. Some of the physical properties of group 16 elements are given in table 7.6. Oxygen and sulfur are non-metals. Selenium and tellurium metalloids, whereas polonium is a metal. Polonium is a radioactive and short-lived, with half-life of 13.8 days. All these elements exhibit allotropy. The melting and boiling point increase with an increase in atomic number down the group. The large difference between the melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as a diatomic molecule, whereas sulfur exists as polyatomic molecule. 7.10.8 Chemical properties. Oxidation states and trends in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, except in the case of OF2, where its oxidation state is +2. Other elements of the group exhibit +2, +4, +6 oxidation states, +4 and +6 are more common. Sulfur, selenium and tellurium are usually show +4 oxidation state in the compounds with oxygen and +6 with fluorine. The stability of +6 oxidation state decreases down the group, and stability of +4 oxidation state increases down the group due to inert pair effect. Bonding in +4 and +6 oxidation state is primarily covalent. Anomalous behavior of oxygen. The anomalous behavior of oxygen, like other members of the P block present in the second period, is due to its small size and high electronegativity. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in water, which is not found in hydrogen sulfide. The absence of d orbital in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalence exceeds 4. Number 1. Reactivity with hydrogen. All the elements of group 16 form hydrides of type H2E. Some properties of hydrides are given in table 7.7. Their acidic character increases from water to H2E. The increase in acidic character can be explained in terms of decrease in bond enthalpy of dissociation of He bond down the group. Owing to the decrease in enthalpy for the dissociation of He bond down the group, the thermal stability of the dissociation of He bond hydrides also decreases from H2O to H2PO. All the hydrides except water possesses reducing property, and this character increases from H2S to H2DE. Number 3. Reactivity with oxygen. All these elements form oxides of EO2 and EO3, where E double bond S, Se, Te or PO. Ozone and sulfur dioxide are gases, while selenium dioxide is solid. Reducing property of dioxide decreases from SO2 to TeO2. SO2 is reducing, while TeO2 is an oxidizing agent. Besides EO2 type, sulfur, selenium and tellurium also formed EO3 types, like SO3, SeO3, TeO3. Both types of oxides are acidic in nature. Number 3. Reactivity towards halogens. Elements of group 16 form a large number of halides of type EX6, EX4 and EX2, where E is an element of the group and X is a halogen. The stability of the halides decreases in the order fluoride is greater than chloride is greater than bromide is greater than iodide. Among hexahalides, hexafluorides are only stable halides. All hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable for steric reasons. Amongst tetrafluorides, SF4 is a gas, SEF4 is a liquid, and TEF4 is a solid. These fluorides have sp3d hybridization and thus have trigonal bipyramidal structure in which one of the equatorial position is occupied by lone pair of electrons. This geometry is also regarded as seesaw geometry. All elements except oxygen form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are diameric in nature. Example are S2F2, S2Cl2, S2Br2, S2Cl2 and Se2Br2. These dimeric halides undergo disproportionation as given below. 2Se2Cl2 gives SeCl4 plus 3Se. Example 7.1. H2S is less acidic than H2E. Why? Solution. Due to decrease in bond dissociation enthalpy down the group, acidic character increases. Now I'm skipping the in-text question for you to solve it later, or you can pause the video and solve it right now. 7.11 Dioxygen. Preparation. Dioxygen can be obtained in the laboratory by the following ways. Number 1. By heating oxygen-containing salts such as chlorates, nitrates, and permanganates. Number 2. By thermal decomposition of the oxides of metal, low in electrochemical series, and higher oxides of some metals. Number 3. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. On large scale, it can be prepared from water or air. Electrolysis of water leads to the release of hydrogen at the cathode and oxygen at the anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Properties. Dioxygen is a colorless and odorless gas. Its solubility in water is to the extent of 3.08 cm³ in 100 cm³ of water at 293 Kelvin, which is just sufficient for the vital role of marine and aquatic life. It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen atom has 3 stable isotopes, O16, O17, and O18. Molecular oxygen, O2, is unique in being paramagnetic in spite of having even number of electrons. Dioxygen directly reacts with nearly all metals and nonmetals except some metals like gold and platinum and some noble gases. In combination with other elements, it is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required as bond dissociation enthalpy of oxygen-oxygen double bond is high. Some of the reactions of dioxygen with metals and nonmetals and other compounds are given below. Please note that I am skipping all the reactions. For solving the reactions on your own, writing it on a pen and paper is a better method. Some compounds are catalytically oxidized. Uses. In addition to its importance in normal respiration and combustion processes, oxygen is used in oxyacetylene welding. In the manufacture of many metals, particularly steel, oxygen cylinders are widely used in hospitals, high-altitude flying, and in mountaineering. The combustion of fuels, example hydrazenes in liquid oxygen, provide tremendous thrust to rockets. I'm skipping in-text questions for you to solve it later, or you can pause the video and solve it right now. 7.12 Simple oxides. A binary compound of oxygen with other element is called oxide. As already stated, oxygen reacts with most of the elements of the periodic table to form oxides. In many cases, one element forms 2 or more oxides. The oxides vary widely in their nature and properties. Oxides can be simple like MgO, Al2O3, or mixed like Pb3O4, Fe3O4. Simple oxides can be classified on the basis of their acidic, basic, or amphoteric nature. An oxide that combines with water to give an acid is termed acidic oxide. For example, SO2 combines with water to give H2SO3, which is an acid. As a general rule, only non-metal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character. The oxides which give a base with water are known as basic oxides. For example, CaO combines with water to give CaOH whole twice, which is a base. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acid as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acid as well as alkali. For example, Al2O3 reacts with acid as well as alkali. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Examples of neutral oxides are CO, NO, and N2O. 7.13 Ozone. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in atmosphere at sea level. At a height of about 20 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet radiations. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone occurs. The product is known as ozonized oxygen. Since the formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. If concentrations of ozone greater than 10% are required, a battery of ozonizers can be used, and pure ozone can be condensed in a vessel surrounded by liquid oxygen. Properties: pure ozone is a pale blue gas, dark blue liquid, and violet black solid. Ozone has a characteristic smell, and in small concentration it is harmless. However, if concentration rises above 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in liberation of heat and an increase in entropy. These two effects reinforce each other, resulting in large negative Gibbs free energy change for its conversion into oxygen. It is not really surprising, therefore, high concentrations of ozone can be dangerously explosive. Due to the ease with which it liberates atoms of nascent oxygen, it acts as a powerful oxidizing agent. For example, it oxidizes lead sulfide to lead sulfate and iodide into iodine. When ozone reacts with an excess of potassium iodide solution buffered against a borate buffer of pH 9.2, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating ozone gas. Experiments have shown that nitrogen oxides, particularly nitrogen monoxide, combine very rapidly with ozone. There is thus the possibility that nitrogen oxides emitted from exhaust system of supersonic jet aeroplanes might be slowly depleting the concentration of the ozone layer in the upper atmosphere. Another threat to this ozone layer is probably posed by use of freons, which are used in aerosol sprays and in refrigerants. The two oxygen-oxygen bond lengths in the ozone molecule are identical, and the molecule is angular as expected with a bond angle of about 117 degrees. It is a resonance hybrid of two main forms. Uses: it is used as a germicide, disinfectant, and for sterilizing water. It is also used for bleaching oils, ivory, flour, starch, etc. It is an oxidizing agent in manufacture of potassium permanganate. I am skipping the in-text question for you to solve it later, or you can pause the video and solve it right now. 7.14 Sulfur allotropic forms. Sulfur forms numerous allotropes, of which the yellow rhombic sulfur, that is alpha sulfur, and monoclinic beta sulfur forms are most important. The stable form at room temperature is rhombic sulfur, which transforms into monoclinic sulfur when heated above 369 Kelvin. Rhombic sulfur or alpha sulfur. This allotrope is yellow in color with melting point 385.8 Kelvin and specific gravity 2.06. Rhombic sulfur crystals are formed on evaporating the solution of rolled sulfur in CS2. It is insoluble in water but dissolves to some extent in benzene, alcohol, and ether. It is readily soluble in CS2. Monoclinic sulfur or beta sulfur. Its melting point is 393 Kelvin and specific gravity 1.98. It is soluble in CS2. This form of sulfur is prepared by melting rhombic sulfur in a dish and cooling it till crust is formed. Two holes are made in the crust and the remaining liquid is poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. This is stable above 369 Kelvin and transformed into alpha sulfur below it. Conversely, alpha sulfur is stable below 369 Kelvin and forms into beta sulfur above this. At 369 Kelvin, both forms are stable. This temperature is called transition temperature. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structures. The S8 ring in both the forms is puckered and has a crown shape. The molecular dimensions are given in figure 7.5a. Several other modifications of sulfur containing 6 to 20 sulfur atoms per ring have been synthesized in the last 2 decades. In cyclo S6, the ring adopts a chair form and the molecular dimensions are shown in figure 7.5b. At elevated temperatures, S2 is dominant species and is paramagnetic like O2. Example 7.12. Which form of sulfur shows paramagnetic behavior? Solution: in vapor phase, sulfur partly exists as S2 molecule which has 2 unpaired electrons in the antibonding p-pi orbitals like O2 and hence exhibits paramagnetism. 7.15 Sulfur dioxide. Preparation. Sulfur dioxide is formed together with a little sulfur trioxide when sulfur is burned in air or oxygen. In laboratory, it is generally generated by treating a sulfite with dilute sulfuric acid. Industrially, it is produced as a byproduct of roasting of sulfite ores. The gas, after drying, is liquefied under pressure and stored in steel cylinders. Properties: sulfur dioxide is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmospheres and boils at 263 Kelvin. Sulfur dioxide, when passed through water, forms a solution of sulfurous acid. It reacts readily with sodium hydroxide solution, forming sodium sulfite, which then reacts with more sulfur dioxide to form sodium hydrogen sulfite. In this reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Sulfur dioxide reacts with chlorine in presence of charcoal, which acts as a catalyst to give sulfuryl chloride SO2Cl2. It is oxidized to sulfur trioxide by oxygen in the presence of vanadium oxide catalyst. When moist, sulfur dioxide behaves as a reducing agent. For example, it converts iron 3 ions to iron 2 ions and decolorizes acidified potassium permanganate solution. The latter reaction is a convenient test for the gas. The molecule of SO2 is angular. It is a resonance hybrid of two canonical forms. Uses: sulfur dioxide is used in number 1, refining petroleum and sugar, number 2, in bleaching wool and silk, number 3, as an anti-clor, disinfectant and preservative. Sulfuric acid, sodium hydrogen sulfide and calcium hydrogen sulfide are manufactured from the sulfur dioxide. Liquid SO2 is used as a solvent to dissolve a number of organic and inorganic chemicals. I am skipping in text questions for you to solve it later, or you can pause the video and solve it right now. 7.16 Oxo acids of sulfur. Sulfur forms a number of oxo acids such as H2SO3, H2S2O3, H2S2O4, H2S2O5, H2SXO6, H2SO4, H2S2O7, H2SO5, H2S2O8. Some of these acids are unstable and cannot be isolated. They are known in aqueous solution or in the form of their salts. Structure of some of the important oxo acids are shown in figure 7.6. 7.17 Sulfuric acid. Sulfuric acid is one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by the contact process, which involves 3 steps. Number 1, burning of sulfur or sulfide ores in air to generate SO2. Number 2, conversion of SO2 to SO3 by reaction with oxygen in the presence of a catalyst. Number 3, absorption of SO3 in H2SO4 to give oleum, that is H2S2O7. A flow diagram for manufacture of sulfuric acid is shown in figure 7.7. The SO2 produced is purified by removing dust and other impurities such as arsenic compounds. The key step in manufacture of H2SO4 is the catalytic oxidation of SO2 with O2 to give SO3 in the presence of V2O5 as catalyst. The reaction is exothermic, reversible, and the forward reaction leads to a decrease in volume. Therefore, low temperature and high pressure are favorable conditions for maximum yield. But the temperature should not be very low, otherwise rate of reaction will become slow. In practice, the plant is operated at the pressure of about 2 bar and a temperature of 720 Kelvin. The SO3 gas from the catalytic converter is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, 2 steps are carried out simultaneously to make the process a continuous one, and also to reduce the cost. The sulfuric acid obtained by contact process is 96 to 98% pure. Properties: sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. Acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with evolution of large quantity of heat, hence care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly to water with constant stirring. The chemical properties of sulfuric acid are a result of the following characteristics. Number 1, low volatility. Number 2, strong acidic character. Number 3, strong affinity for water. And number D, ability to act as an oxidizing agent. In aqueous solution, sulfuric acid ionizes in 2 steps. The larger value of Ka means that H2SO4 is largely dissociated into H plus and HSO4 minus ions. Greater the value of dissociation constant Ka, stronger is the acid. The acid forms 2 series of salts, normal sulfates such as sodium sulfate and copper sulfate, and acidic sulfates like sodium hydrogen sulfate. Sulfuric acid, because of its low volatility, can be used to manufacture more volatile acids from their corresponding salt. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid, provided the gases do not react with the acid. Sulfuric acid removes water from organic compounds. It is evident by its charring action on the carbohydrates. Hot concentrated sulfuric acid is a moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acid. Both metals and nonmetals are oxidized by concentrated sulfuric acid, which is reduced to SO2. Uses: sulfuric acid is very important industrial chemical. A nation's industrial strength can be judged by the quantity of sulfuric acid it produces and consumes. It is needed for the manufacture of hundreds of other compounds and is also in many industrial processes. The bulk of sulfuric acid produced is used in manufacture of fertilizers. Other uses are in petroleum refining, manufacture of pigment, paint and dye stuffs intermediate, detergent industry, metallurgical applications, cleaning metals before enameling, electroplating and galvanizing, storage batteries, manufacture of nitrocellulose products, and as a laboratory reagent. Example 7.13. What happens when number 1, concentrated H2SO4 is added to calcium fluoride, number 2, SO3 is passed through water? Solution: number 1, it forms hydrogen fluoride, and number 2, it dissolves SO3 to give H2SO4. Again, I am skipping the in-text questions for you to solve it later, or you can pause the video and solve it right now. So that is for today, and we will be continuing with Group 17 elements in the next audiobook. Till then, subscribe to the channel and stay tuned. Thank you.